Welcome to the Explainer. Today, we're taking a massive leap forward in our programming journey. We're finally moving away from those messy, ad hoc scripts, and we're stepping into the world of professional, structured, object-oriented Java code. Honestly, think of it like graduating from basic functional scripts straight into enterprise-grade engineering. It's a huge step. Today, we're going to level up and learn exactly how the pros build robust software. And we'll do it by constructing our very own real-world inventory management system. Okay, let's dive right into this because this right here is the fundamental question every single developer faces. You start a project, it's small, it's perfectly manageable, but then you add more features, more products, more operations, and suddenly your code just becomes this incredibly tangled web. If you want to update one tiny thing, you end up breaking three others. Right, so how do you actually manage this kind of complexity at scale without rewriting everything from scratch every single time? Well, thankfully, Java gives us a really powerful toolkit to solve exactly this problem. To get there, we've got a really clear roadmap for this explainer. First, we'll cover the philosophy of coding smarter, not harder. Then, we'll master three specific pillars of object-oriented programming: inheritance for sharing blueprints, interfaces for mastering modular operations, and packages for organizing your inventory. Finally, we'll look at the future of your code. Let's get into it. Section 1. Coding smarter, not harder. Section 2. Inheritance. Sharing the blueprint. Coding smarter, not harder, it's really the dividing line between a total novice and a seasoned professional. It's all about drastically saving time and reducing your errors. To visualize this, imagine you're running a massive physical warehouse. You absolutely wouldn't design a brand new physical storage bin from scratch for every single individual item you sell, right? That would be crazy. Inheritance is the software mechanism that gives us that standard blueprint so we can achieve true code reusability. It lets us design class structures that actually derive from one another. The whole goal here is to build an efficient representation of product categories so we literally never have to copy and paste identical code across multiple files ever again. To actually use inheritance effectively, there are a few core mechanics working behind the scenes that you've got to master. We have different types of inheritance structures. We have method overriding, which is super cool. It lets a child class change a behavior it inherited from its parent. We use the super keyword to talk directly to that parent class. And then we have the abstract and final keywords, which strictly dictate what can be passed down and what is absolutely locked in place. Think of these as the dials and levers that control exactly how traits flow through your software. Now, what's really interesting about this is how brilliantly it illustrates a real-world application. Our base class here, which is just called product, acts as our generic blueprint. Every single item in our warehouse has a product ID and a product name, so we write that logic exactly once. Meanwhile, our derived class, electronic product, absorbs all that generic data and then simply adds its own specific details right on top, things like a brand and a warranty period. When you go to actually display the complete product details in your app, it seamlessly pulls from both. It's just elegantly simple. Write once, reuse everywhere. Seriously, if you take away anything from this explainer, let it be this phrase. Because quite frankly, if you manually duplicate your code 100 times for 100 different products, the only thing you're really going to achieve is a severe case of carpal tunnel syndrome. Inheritance just fundamentally changes the way we work, making our code lean, clean, and incredibly powerful. Section 3. Interfaces, mastering modular operations. So our products don't just sit there gathering dust. Stock arrives, items ship out. We need actions. But here's the catch. Java has a really strict rule where a class can only inherit from one single parent class at a time. So we need a workaround for a product to inherit behaviors from multiple different sources. That is exactly where interfaces come in. An interface is a concept we apply to basically achieve multiple inheritance and promote highly modular design. Instead of being a structural blueprint for an object, an interface is a strict operational contract. It basically defines the what without worrying at all about the how. Let's see this in action to make it a bit more concrete. We establish an interface contract, and we'll call it inventory operations. Now, this contract demands two very specific methods: add stock and remove stock. It doesn't actually write the code for them. It just says, hey, if you want to be part of this inventory system, you absolutely must be able to do these two things. Then, our actual class implementation, product inventory, steps up and writes the real code to perform those stock management operations. By separating the contract from the implementation like this, we create these fantastic, reusable plug-and-play modules that make our overall software incredibly flexible. Section 4. Packages, organizing your inventory. Now, as our system grows to handle thousands of different items, we need distinct aisles and shelves to prevent absolute chaos. In Java, a package is quite literally a way of grouping those related classes, interfaces, and even sub-packages all together. This is the ultimate tool for writing a genuinely well-structured application. It completely prevents naming collisions. So, for example, you can have two totally different classes, both named box, as long as they live in different packages, and it massively improves overall code modularity. It is the absolute key to managing scale. Before you start organizing everything, you do need a basic grip on a few core mechanics. You need to know how to define a package right at the very top of your file. You should understand the difference between built-in Java packages and your own user-defined ones. You really need to follow standard naming conventions. We usually use reverse domain names for this. And you need to know how to create them in your file system. But most importantly, you need to know how to actually access a package when you need to use the code hidden inside it. Let's move to a practical scenario and see how this builds. Step 1. We create a custom, user-defined package, and we name it inventory.management. Think of this like dedicating a whole specific wing of our warehouse purely to management tasks. Step 2. We take that base product class we built earlier, and we neatly store it right inside this package. Step 3. We switch over to a completely different Java program. Maybe it's our main dashboard screen. And we use the import keyword to bring that package in so we can easily display our product information. We are keeping our workspace completely clean and only loading the specific tools we need exactly when we need them. Section 5. The future of your code. So the crucial point is this. We started out with messy ad hoc scripts. And now? Now we have a cohesive professional toolkit. Inheritance gives you those reusable blueprints so you literally never have to write the same thing twice. Interfaces give you strict modular operations so your classes know exactly what they need to do to interact with one another smoothly. And packages provide the filing cabinet that keeps your rapidly growing software ecosystem beautifully organized. When you combine these three pillars, you stop writing mere scripts and you start engineering true software applications. You now hold the keys to professional object-oriented design. You know how to reuse code efficiently, demand modularity, and organize at massive scale. So the only question left for you is, now that you have the blueprints, what will you build? And perhaps more importantly, as you start adding things like databases and multi-threading down the line, how will these structural foundations hold up? Get out there, open up your code editor, and start constructing your own brilliantly organized systems. Thanks so much for joining me on this explainer, and happy coding.